this morning to talk with you about Ramanujan's Lost Notebook. I'd like to begin with this quote from the Bhagavad Gita. Through long lapse of time, this knowledge was lost. I think he is talking about the lost notebook of Ramanujan. But now, as you are devoted to truth, and the you here, I think, is George Andrews, who found the lost notebook, I will reveal the supreme secret. So I'll tell you something about these secrets, or what one can find in the lost notebook. So the organization for my lecture is roughly as follows. I'll spend about 10 or 15 minutes describing the discovery and history of the lost notebook and generally what one can find in it. And then for the second third of my lecture, I'll describe the topics that one can find in the lost notebook, just saying a few words about several of the topics. And then in the third part of my lecture, I've decided to concentrate on one topic in the lost notebook, namely continued fractions. And if you are not familiar with continued fractions, you need not worry, because I will be giving an introduction, and I really won't prove anything about continued fractions. So I usually begin my lectures with a photograph of Ramanujan. There are only 4 photographs that exist of him, and this is by far the most famous. It's his passport photo. It was taken just prior to his return to India from England. At this time, he was very ill. He could not go to the photographer to have his picture taken, and so the photographer had to come to the nursing home to photograph him. So Robert Rankin, who was the last PhD student of G.H. Hardy, told me that Hardy had told him that Ramanujan was photographed here in his bathrobe and pajamas at the nursing home, not a suit coat as it might appear from looking at the photograph. So let me begin then with George Andrews finding the lost notebook. So at the invitation of Dr. Lucy Slater in the spring of 1976, Andrews visited Trinity College, Cambridge, and she suggested to him that he might find it worthwhile to examine the papers left by the late G.N. Watson. So while he was examining these papers, he found a box containing 138 pages of results in Ramanujan's handwriting. Andrews had written his PhD thesis on Ramanujan's Mach theta functions. These are among the last creations of Ramanujan. He wrote one letter to Hardy after he returned to India, and in this letter he described the Mach theta functions. So he recognized Ramanujan's handwriting. He saw the Mach theta functions appearing in this manuscript, and so he knew immediately that these results or pages were from the last year of Ramanujan's life. So how did then this work of Ramanujan get cataloged amongst Watson's papers? So let me say a few words about Watson. So Watson became interested in Ramanujan's work shortly after the collected papers, the published papers, were brought together and published in 1927. So with the collected papers were the first 2 letters that Ramanujan wrote to Hardy. And in these letters, Ramanujan stated about 120 results without proofs. And so the publication of the collected papers then produced a flurry of papers by English mathematicians proving results from these 2 letters that Ramanujan wrote to Hardy. And chief among these people who wrote such papers was Watson. So Ramanujan had recorded his results in notebooks before he departed for England, and Hardy had strongly urged that these notebooks be edited. So by editing, he meant that if a result is known, then just a source for its proof could be cited, but if a result is not known, then we should try to prove the result. So in the late 1920s, Watson and B.M. Wilson agreed to start editing Ramanujan's notebooks. They never completed the task. Watson worked on the project for about 10, 15 years, and Wilson unfortunately died prematurely. But during this time, Watson wrote over 30 papers arising from Ramanujan's work, mostly in his notebooks. So he knew more about Ramanujan's work than anyone at that time. Well, Watson was a professor at the University of Birmingham for most of his career. He died in 1965 at the age of 79. And after he died, two people in particular visited his widow. And one of them was Robert Rankin, whom I had just mentioned a few moments ago. So Rankin had actually succeeded Watson as the Mason Professor of Pure Mathematics at the University of Birmingham upon Watson's retirement, but had since gone on to the University of Glasgow to become Professor of Mathematics there. So he and Mrs. Watson discussed what they should do with these papers, and it was decided that since her late husband had been a fellow at Trinity College, Cambridge, and since Ramanujan had been the first Indian fellow at Trinity College, Cambridge, that the best thing to do would be to sort through these papers, and those that were worth preserving be sent to the Trinity College Library. So over a period of more than 3 years, Rankin sorted through these papers, and on December 26, 1968 to be precise, the Ramanujan material was sent by Rankin to Trinity College. The second person that visited Mrs. Watson was J.M. Whittaker. J.M. Whittaker was the son of E.T. Whittaker, and many of you have probably heard of the text, A Course in Modern Analysis, or used it by Whittaker and Watson. It's probably the most useful text, most cited text in analysis in the 20th century. So J.M. Whittaker was also a mathematician and a physicist, and as he later described it, Mrs. Watson took me upstairs to her late husband's attic floor office, where the floor was covered to the depth of about a foot of papers. And you could only sort of make lucky dips into these papers, and one of his lucky dips produced the Ramanujan material that Andrews had found. So Whittaker wrote an obituary of Watson for the Royal Society and Rankin for the London Mathematical Society, but neither of them realized the importance of these pages in Ramanujan's handwriting, and so never mentioned Ramanujan's work in the obituaries. So the material from Watson's estate on Ramanujan's work just sat there for about 7.5 years then before George Andrews then rediscovered it. So it was not really lost. It was at least known to the catalogers and Rankin and Whittaker, and it really wasn't a notebook, but if I had been Andrews in view of the fame of the earlier notebooks, I would have done the same thing and called this material Ramanujan's lost notebook. So now the question is, how did this material reach Watson? Well, Ramanujan died in 1920, and as I indicated, Hardy strongly urged that not only his published papers, but also his notebooks and any other papers that could be found be brought together for publication. But the London Mathematical Society was not in good financial condition at that time, so in 1927 only the published papers were brought together and not the notebooks or any other papers. So we know that on August 30th, 1923, the registrar at the University of Madras sent to Hardy a large packet of material, including copies of the notebooks. So almost certainly this large packet of material contained then the lost notebook. So Hardy had this in his possession then evidently for many years. He did not give it to Watson evidently before Watson's interest in Ramanujan's work evidently waned in the late 1930s. The reason we say this is that the last two papers that Watson wrote on Ramanujan's work were on the Mach theta functions. And in these two papers that Watson wrote, he said, well, it's surprising that Ramanujan didn't discover these third-order Mach theta functions that I'm giving you, which naturally fit in with the third-order Mach theta functions in the last letter that he wrote to Hardy. Well, if he had the lost notebook with him, he would have seen, indeed, those functions do appear in Ramanujan's work. They're right there in the lost notebook. Then Watson also said, well, the third-order Mach theta functions satisfy beautiful transformation formulas. I've worked very hard on the fifth-order Mach theta functions, and I'm convinced they do not satisfy transformation formulas. Well, if he had had the lost notebook, he would have seen that Ramanujan did derive the transformation formulas for the fifth-order Mach theta functions. So Hardy died in 1947, so evidently sometime between the late 1930s when Watson wrote these two papers and his death in 47, Hardy must have passed on the lost notebook to Watson. Well, I think then that's the history of the lost notebook. It was published in 1988 by Narosa, New Delhi. And by that time, they found some other partial manuscripts of Ramanujan in the libraries at Trinity College in Cambridge. And there were some handwritten copies by Watson of manuscripts of Ramanujan as well. Most of the manuscripts actually do exist. At the time of the publication of the Narosa volume, the originals evidently were not known to the publisher. And then some of the letters that Ramanujan wrote to Hardy from nursing homes have been preserved, and they are also found in the Narosa publication. So the original lost notebook has about 650 claims of Ramanujan, all without proofs. There are hardly any words at all in the lost notebook. So let me now tell you about some of the topics that one can find in the lost notebook. So here is a page from the lost notebook. So this is actually one of the better pages. It's more visible and readable than some pages. You'll just have to accept my word on this, that this is a very interesting page. It has a lot of very interesting results. So this page is much more difficult to read, and the reason it's difficult is that the photographer for Narosa actually photographed two sides of the page at once. The page was, so these pages that Ramanujan wrote on in the lost notebook are varying qualities and sizes and types. So a few of the pages are parchment paper. So here the photographer was photographing both sides of this thin piece of parchment paper that Ramanujan was working on. The librarian at Trinity College, Cambridge, when she made a copy of the lost notebook for Andrews, was much more careful on the copy that Andrews has. Both sides are very readable. I might just tell you an interesting incident in regard to Andrews finding the lost notebook. He was obviously very, excited in finding this and wanted a copy right away. And so the librarian said, well, we'll should be able to make a copy with it, for you in the next couple weeks. And so Andrews was going to leave in a few days, and he said, that's fine. It's okay if you send me a copy. Well, the next day he came back to the library and he saw on the librarian's desk a package addressed to him. And it took a while for him to convince the librarian that it was okay if he just gave him, she just gave him that package directly and, you know, save money by not mailing it to him. So he did bring the lost notebook back with him when he came to the U.S. So the main topic in the lost notebook are Q series. So let me just define what a Q series is. Generally, Q series have products in them of this type. 1 minus a, q to the j, j running from 0 to n minus 1. So n would be the index of the subends. So if the base q here is known or doesn't change, we just leave off the q in the notation. And then this is the infinite version of the q products. So probably the most useful and famous theorem in the theory of Q series is what's called the Q binomial theorem. The reason it's called the Q binomial theorem is that if you take the A appearing here in the series, replace it by Q to the A, and let Q tend to 1, then you get the familiar binomial series with calculus. So many of the theorems in the theory of Q series are sort of analogs of theorems about functions that are elementary or special functions. So closely associated with Q series are theta functions. And generally, these are often considered part of the theory of Q series, although they do not have the products that I just showed you in them. So this is Ramanujan's notation for a general theta function. And these are the three most useful and special cases. And I'm using Ramanujan's notation for all three of them. So in this one, we generate the squares here. These are the triangular numbers. And in this one, these are the pentagonal numbers. So theta functions satisfy lots of identities. And a particular kind of identity is actually called the modular equation. So there are various modular equations in the lost notebook. So there are results of what are called false theta functions. So a false theta function is like a theta function, but you change the sign in infinitely many terms. Now, of course, if you just do this at random, you won't get anything interesting. But if you do this properly, you might get something interesting. And here are two examples. So if you remember the previous screen, I had a theta function, psi of q, as the sum of q to the n plus 1 over 2, containing the triangular numbers. So here, then, we just put in a minus 1 to the n, which changes the sign of all the negative, or all the odd index terms. So there are some number of results on what are called partial theta functions. And this topic is something which is really new in the lost notebook. There really doesn't exist any other literature, previous literature, in this subject. So a partial theta function is like a theta function, but we only take part of the terms. So again, you can't just do this at random. Usually the terms you take are the terms with non-negative index. Okay, so here, if on the left side, if we had summed from minus infinity to infinity, we'd have a theta function. But now we're just summing from 0 to infinity. Well, this identity is actually found in Ramanujan's lost notebook, and points out the fact that many of the identities in the lost notebook have combinatorial interest. So I'll explain more about partitions in just a few minutes, but let me just briefly mention what's going on here. So here we're actually generating partitions into distinct parts, and in the denominator we're generating partitions into even parts. And somehow most of these partitions are now being canceled on the right-hand side, because the powers of q are just in a very thin sequence, the squares on the left-hand side. So this is the beautiful thing about many of the results in the lost notebook. They have beautiful combinatorial implications, and finding combinatorial proofs is often very, very challenging. Eisenstein series appear prominently in the lost notebook, and these are the three basic Eisenstein series. In more modern notation, Q and cap R are E4 and E6. So in the modern notation, these are in the theory of modular forms, and E4 and E6 actually generate the field of modular forms in the full modular group. So there are various identities and properties for these Eisenstein series. Here is a representation for the Eisenstein series Q. Q, in terms of the f of minus q, that was the third of the special cases I gave you. This is an interesting series. It arises from really sort of differentiating the pentagonal number theorem series. And there's a page in the lost notebook devoted to this series. And in particular, Ramanujan shows that T sub 2k is QQ sub infinity, which actually is just f of minus q, times a polynomial in P, Q, and R. So I've just given the first three cases here. So from that first example, it's sort of an interesting corollary. Ramanujan didn't actually write this down, but it's immediate from his first special case. So let me just briefly give this to you. Sigma of n is the sum of the divisors of n. And we write sigma 0 equals minus 1 over 24 just for convenience. So then this result says that if we take this alternating sum of the sigma function, summed over all pairs j and k, such that this sum is equal to n, then that sum is almost always 0. It's only not equal to 0 if you have a pentagonal number, or if you have a generalized pentagonal number. The generalized ones being where you take plus or minus in the sign. So there are lots of results of what are called basic hypergeometric series. There's this is a definition of a 2 phi 1 basic hypergeometric series. So again, these are cube products in the sum n. And this is a Heine's transformation. Heine is one of the original founders of the theory of Q series in the 1840s. This is a transformation for the 2 phi 1. And there are a number of results in Ramanujan's notebooks, lost notebook, that arise from Heine's transformation and other basic theorems in the theory of basic hypergeometric series. And almost all of these results are new, but you can prove them using basic results in basic hypergeometric series theory. So one of the things for which Ramanujan is very famous for is what is called his 1 psi 1 summation. This is actually in his earlier notebooks. So what we need to do to state that theorem is to define AQ sub n for negative integers as well as positive integers. So we can do that using this formula. So if n is a non-negative integer, it reduces to the previous definition I gave you. So what we have here in Ramanujan's 1 psi 1 summation then is an analog of the Q binomial theorem for bilateral series. So here our sum goes from minus infinity to infinity. Here we have 8 infinite products on the right-hand side. You might think that that looks complicated, but in the theory of Q series, it's actually quite easy to work with. So there are a number of results in the lost notebook that arise from his 1-psi-1 summation theorem. Okay, so let me now discuss partitions, which also appear prominently in the lost notebook. So I'll assume you do not necessarily have a background in partitions, so let me begin at the beginning, so to speak. So P of n, the partition function, is the number of ways of writing n as a sum of positive integers. So for example, P of 4 equals 5, because as you can see, there are 5 ways we can write 4 as a sum of positive integers. We don't count different orders as being distinct. And a generating function for the partition function P of n is just 1 over QQ sub infinity. So remember that QQ sub infinity is 1 minus Q, 1 minus Q squared, 1 minus Q cubed, etc. So if you take each of those factors and expand them in infinite geometric series, you get this. So the first series then generates the 1s that appear in a particular partition. The second series generates the 2s, etc. So if you want to get the contribution from 2 plus 1 plus 1, you take the term n1 equals 2 from this series, but you got 2 1s, and n2 equals 1 from this series, because you have 1, 2. And then from the other series, you just take the 0 term. So you get all of the partitions once and only once, that is uniquely in this fashion. So we indeed have the generating function for partitions here. So there are 2 very famous identities called the Rogers-Ramanujan identities for Q series that have very interesting partition theoretic interpretations. So let me just, so the Rogers-Ramanujan identities are these 2 identities for the 2 Q series you see at the top of the screen. So let me just tell you about the combinatorial interpretation of one of them. So on the left-hand side, I'll leave this for you as an exercise, that is in the series definition, we're generating partitions into parts differing by at least 2. To see this, I'll give you a hint. Write n squared is 1 plus 3 plus dot 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 up through 2n minus 1. So I think most of you are familiar with that formula. Okay, so again, on the left side, we're generating partitions into parts differing by at least 2. And on the right-hand side, I think you can see we're differing by, have partitions with parts congruent to 1 or 4 modulo 5. Because this product is 1 minus q, 1 minus q to the 6th, 1 minus q to the 11th, etc. This is 1 minus q to the 4th, 1 minus q to the 9th, etc. So in other words, we're getting parts congruent to 1 or 4 modulo 5. So here is a numerical example. So if you take 8, those are the 4 partitions you see at the bottom of the screen into parts differing by at least 2. And then in the second line, we have the partitions of 8 into parts congruent to 1 or 4 modulo 5. So the reason I give you this is not in the lost notebook, although there are results arising from it in the lost notebook. There are many other identities that Ramanujan has of this type in the lost notebook. And note that I put Slater's name on this. So she is the one that invited Andrews to Cambridge. She published a paper in the early 1950s giving lots of identities of this type. And a number of her identities are actually found in the lost notebook. So let me say now something about continued fractions. So continued fraction is something which just looks like this, where the dots indicate that this continued fraction might be infinite. So we usually use this more compact notation where the plus signs appear in denominators to indicate that this is not a sum, but a continued fraction. And the most famous of all continued fractions is the Rogers-Ramanujan continued fraction. So it's this very simple looking continued fraction. You might ask, well, what's this q to the 1/5 doing there? Looks a bit out of place. Well, this continued fraction sort of lives in the homes of elliptic functions and modular forms, and for purposes which I won't go into, it sort of belongs there when you look at those theories. There's another continued fraction besides the Rogers-Ramanujan continued fraction that's extensively examined in the Lost Notebook, and this is my terminology. I call this the enigmatic continued fraction, just because its properties are much different than those properties of the Rogers-Ramanujan continued fraction. So hopefully at the end of my lecture I'll say something in more detail about this continued fraction as well. So there are some asymptotic expansions of continued fractions, some general theorems on continued fractions in the Lost Notebook. So let me go back to the partition function. So these are three famous congruences for the partition function that Ramanujan discovered. Well, in 1944, Freeman Dyson said that I'm not very satisfied with the proofs that we have of these congruences. There must be some combinatorial explanation or interpretation of these congruences. So what Freeman Dyson did was to define the rank of a partition as the largest part minus the number of parts to explain combinatorially these divisibility properties. So if you take the partition 4 plus 1, the rank of that partition would be 4, because that's the largest part, minus 2, because there are 2 parts. That is 4 minus 2, or 2. So that would be the rank of that particular partition. So Dyson observed that if you take the partitions of any number of the form 5n plus 4, and you looked at the residue mod 5 for the ranks of these partitions, they divided themselves into equinumerous classes. So not only does this definition give you a combinatorial explanation of the congruence, if you prove what you have observed, it also proves the congruence. Because if you have 5 classes with the same number in each class, then obviously the total number is a multiple of 5. And the same thing Freeman Dyson observed for the second congruence. In other words, if you look at the ranks of all the partitions of 7n plus 5, they divide equally into 7 equinumerous classes according to the residue of these ranks. But unfortunately, his observation didn't work for the partitions of 11n plus 6. So Dyson then conjectured there must be some other partition statistic, which he called the crank, which would explain then this partition congruence. Well, in the Lost Notebook, Ramanujan actually has the generating function for ranks and cranks. So the crank was actually found in 1988 by George Andrews and Frank Garvin. But then afterwards, they discovered that in the Lost Notebook, there are many results on ranks and cranks. So Ramanujan never wrote out any definition of a rank or a crank of a partition, but he did write out the generating functions for them, and he had lots of properties for the ranks and cranks from using the generating functions. So here is a page of just a scratch work. There are about 20 or 30 pages of scratch work in the Lost Notebook, and I can't really explain what was going on here, but there are hints that Ramanujan was calculating cranks here. And I think maybe perhaps all of the scratch work that one finds in the Lost Notebook pertains to cranks of partitions. So let me continue on a little bit with partitions. Here is another generating function for partitions. So I'll leave it to you as an exercise to show, in fact, that the series on the left side also generates P of n. So what you have to do is to write down what's called a Ferris graph for the partition. That is, you write, put dots down for each part of the partition, and you put them in descending order, and you make things flush at the left column. And then what you do is to pick out the largest square from this graphical representation, and that largest square is indicated by the n squared here, the number of dots you would have in a square of size n. Well, in the theory of Q series, if you make just sort of one minor looking change, you actually change, in most cases, the behavior of the series a lot. So here, if we just make one minor change in this series here, by the way, this identity goes back to Euler, and replace the q by minus q, you get something entirely different. Here we have that the coefficient of q to the n is the number of partitions of n of even rank minus the number of partitions of n of odd rank. And this function here is a Mach theta function. This is a third order Mach theta function. And in his lost notebook, Ramanujan has identities and properties of this particular function. Here is another Mach theta function, again with a partition theoretic interpretation of the coefficients. So here the coefficient of q to the n is the difference of the numbers of partitions of n into distinct parts with even rank, and the number of partitions of n into distinct parts with odd rank. Yeah. So that's another example of a third order Mach theta function. So here is, I'll just quote very briefly from the last letter that Ramanujan wrote to Hardy. He said, "I discovered very interesting functions which I call Mach theta functions. Unlike the false theta functions studied partially by Professor Rogers in his interesting paper, they enter into mathematics as beautifully as the ordinary theta functions." And in the last 8 years, there's been an enormous amount of work that's been accomplished on Mach theta functions. And the principal researchers have been Xander Swagers, Ken Ono, and Katrin Brigman. And they have put the Mach theta functions into what are called in the formulation of weak Moss waveforms. And so now we have a much better understanding of them. However, although we have a much better understanding of Mach theta functions, we still have no idea how Ramanujan thought of them. So in other words, our proofs of the identities and properties in the lost notebook that Ramanujan stated for these functions are nowhere near probably what Ramanujan had. We just don't know what his reasoning was. So the results on integrals and complete elliptic integrals. Here, let me show you one really challenging problem you can give to your calculus students. So f of minus q, that's q sub infinity, that's the pentagonal number theorem. Ramanujan defines a function v as the quotient of these functions. Then he states this integral here, identity. So here we have an integral of these functions f, and then here these are incomplete elliptic integrals that I defined in the previous screen. So you have a difference of incomplete elliptic integrals. So very strange limits here. Note, we'll give a proof for this identity when q is 0. When q is 0, v is 0. And here we have an integral from 0 to 0. That's 0. Here, v is 0. So in other words, you get the same limit in the denominator as the numerator. So this is extremely difficult to prove. And if any of you can find a proof of this, we would just love to see it. We do have a proof of it, but it's difficult. So the integrals of Q products, the integral transforms, special integrals. This integral is examined on a page in the lost notebook. He gives several properties. It's a very beautiful integral because it has properties of theta functions, although it certainly doesn't look like a theta function. So theta functions satisfy transformation formulas, or say the variable w goes into 1 over w. So here in this integral, here's the 1 over w in the index. So w goes into 1 over w and also goes into 1 over w in the argument. Then in transformation formulas, there's this square root w that appears. Here it appears as well. And here it appears in the 1 over w place. So it's a very interesting elementary integral. And again, you might try proving this as an exercise. So the results on Dirichlet series, on Euler products, infinite series identities of approximations, numerical calculations, couple entries on Diophantine equations. There are some few pages on elementary mathematics, a mathematics that's understandable by 8th or 9th grade algebra students. So I don't have much time remaining, but in the last maybe 10 or 12 or 15 minutes, I will just confine myself to one topic, namely continued fractions. So I'll begin then with Ramanujan's first letter to Hardy, written on January 16, 1913. So this is a very beautiful identity. Let me convince you of that. This is the Rogers-Ramanujan continued fraction, but with the argument q equals x to the 5th. And here is the continued fraction itself. So what Ramanujan is stating is an identity for the 5th power of this continued fraction in terms of the continued fraction where the argument is replaced by the 5th power. So it's a really beautiful identity, and you note the symmetry in the polynomials in the numerator and denominator. Then he evaluates the continued fraction exactly if q is e to the minus 2 pi. For some reason, he put the 5th power of e to the minus 2 pi on the right side here. So it's a very nice evaluation in closed form. And here is the evaluation when q is minus e to the minus pi. Very similar evaluation. And then he says, this continued fraction can exactly be found if n is any positive rational quantity. So in the first example, we have then that n is equal to actually 4. Then in his second letter to Hardy, Ramanujan also stated some properties of this continued fraction. Here he used a different notation, as you see. So this is really a very beautiful identity. He has the continued fraction, and here is that exponential, which he didn't put in, or that power of q. So the golden ratio plus this times the golden ratio plus the same function, but now evaluated at beta instead of alpha, but with the condition that alpha beta be pi squared. Then that product is simply 5 plus square root 5 over 2. And a very beautiful, surprising result. And again, he says it's always possible to find the value of this continued fraction. So there are two claims that he made in both letters, and this is one of those two claims that he made in both his first two letters. And he said in similar continued fraction, if n be any rational quantity, he doesn't actually give the continued fraction. And then he gives the value of the Rogers-Ramanujan continued fraction now at e to the minus 2 pi square root 5. So you see it has a little bit more complicated value here. And he says the above theorem is a special case of a theorem on this continued fraction. So he's added a parameter. This is now called the generalized Rogers-Ramanujan continued fraction in the literature, which is a particular case of this continued fraction. So he's added another parameter, which is a particular case of a general theorem on continued fractions. But he stops here, and he doesn't tell us what the general theorem on continued fractions is. Well, Hardy wrote to Ramanujan on March 26, 1913, which happens to be the day on which Paul Erdős was born. So my guess is that Hardy didn't know that Paul Erdős was being born on that day. This is the days before email, and so Erdős's parents couldn't write Hardy and say, well, I thought we should tell you that Paul Erdős is being born today. So if I may add a personal note, my mother was celebrating her first birthday on this day, and she's now 99 years old. So Hardy wrote to Ramanujan, what I would like above all is a definite proof of some of your results concerning continued fractions of this type. And I'm quite sure that the wisest thing you can do in your own interest is to let me have one as soon as possible. And Ramanujan did not write the paper that Hardy asked him to write. So on December 24th, Hardy again wrote to Ramanujan, if you will send me your proof written out carefully so that it is easy to follow, I will, assuming that I agree with it, of which I have very little doubt, try to get it published for you in England, write it in the form of a paper on this continued fraction, giving a full proof of the principal and most remarkable theorem that the fraction can be expressed in finite terms when x is e to the minus pi square root n, when n is rational. So I think that Ramanujan never wrote this paper that was requested by Hardy just because he did not have a firm proof of this statement. This is actually very, very difficult to prove, and proof actually involves maybe mathematics that was unknown in Ramanujan's time. But Ramanujan clearly observed that in many cases, for many values of n, he could evaluate the continued fraction. So this is the notation we usually use for the continued fraction. And if you've had a course in elementary number theory or have evaluated some elementary continued fractions, you've actually evaluated maybe continued fraction at 1 or minus 1. Okay, I'm going to skip this next part. So there are a couple identities for R of Q, which are found in Ramanujan's earlier notebooks. And f of minus q is, again, the pentagonal number theorem series. So you see from these identities that if for a particular value of q, you could evaluate the right-hand side, then you could evaluate the left-hand side by just solving a quadratic equation. So the problem of evaluating the Rogers-Ramanujan continued fraction then boils down to our ability to then evaluate either of these quotients for a particular value of q. Well, there is a page in Ramanujan's lost notebook where he gives a table here of values of the Rogers-Ramanujan continued fraction. Here he uses the notation f. So he's indicating that he can really evaluate the continued fraction for all these values of the argument. But remember that Ramanujan is dying, he's running out of time, so he just gives 3 of the values and then goes on to some other topic. Well, let me actually sort of give you a couple of those values in latent form. So here is one of them. It's the value of the continued fraction at minus e to the minus pi square root 7/5. And here is another value at e to the minus pi square root 9/5. And the reason I put it in this form is that you can see he solved the quadratic equation in order to, just from the nature of what you would see here, you can see he solved the quadratic equation in order to evaluate the continued fraction. Well, to evaluate the continued fraction, as I said, you need to evaluate the quotient on the right-hand side. And here is where difficulties arise. You have to use what are called values of class invariance. Now, Ramanujan actually knew about class invariance, but evaluating them is very difficult. So I'll just look at one of the class invariants here. So Ramanujan sets chi of q to be minus q squared sub infinity. So that would be the product 1 plus q, 1 plus q cubed, 1 plus q to the fifth, etc. And then if q is e to the minus square root n, so that's exactly the argument that appears in Ramanujan's letters to Hardy, then we have what are called these are class invariants now. And they turn out to be algebraic numbers in all cases now. And then if you take in the theory of elliptic functions, the elliptic parameter k, and replace k by, or k squared by e to the minus pi square root n, this is what's called a singular modulus now. And singular moduli are related to class invariance by these equations. So Ramanujan in his notebooks evaluated many of these class invariants. So here are some of them, these algebraic numbers. And this one, Ramanujan stated in his second letter to Hardy. So it's a very complicated number. It was actually proved by Watson in a paper he devoted just to this evaluation. And he said in his paper, I think Ramanujan guessed it. So how many people here believe that Ramanujan guessed this one? Okay, well, I will take the survey here, and when I cross over and talk with Watson, I'll tell him that not many people believe that Ramanujan guessed this one. So anyway, these are the kinds of things one has to calculate in order to evaluate the Rogers-Ramanujan continued fraction. So let me tell you about another result in the lost notebook, which looks very complicated, but I'll try to convince you that it really is very interesting. So Ramanujan states some identities involving P and Q, but he actually doesn't give the definitions of P and Q. So I assigned this problem to one of my graduate students some years ago, and he figured out what the P and Q are. So these definitions do not appear in the lost notebook. But these identities do appear without the definitions of P and Q. Okay, so they're rather complicated identities for theta functions. However, if you take lambda to be equal to 1, then P actually reduces to 1 over R of Q, the reciprocal of the Rogers-Ramanujan continued fraction. And Q, cap Q, reduces to just R of Q, the Rogers-Ramanujan continued fraction. So if you take those three identities claimed by Ramanujan, these are then the identities that you get. So you'll notice that the first and third are those two identities from the earlier notebooks for the Rogers-Ramanujan continued fraction that are used to evaluate the continued fraction. Now it happens that the second identity is just trivial in this case because it's, of course, obvious that the product of P and Q is equal to 1. So the reason I state this is that I think this sort of points to some things that Ramanujan's work will have value for the future, in that here we have two variable generalizations of these two identities for the Rogers-Ramanujan continued fraction. And I think some of the other results that Ramanujan has found may have also two variable generalizations. So that's sort of a field that might be just opening up for the future. Well, I'm sort of running a bit out of time. Maybe I'll just say a few words about this page in the lost notebook. So I promised to say one word about the enigmatic continued fraction. So let me just give you one of the results on this last page. So it involves values of the Riemann zeta function and Dirichlet L function. So for those of you not familiar with the Riemann zeta function, the Riemann zeta function, zeta of s, is the sum of 1 over n to the s, n running from 1 to infinity, where the real part of s is bigger than 1. And a Dirichlet L function is the same kind of definition, but you put in the numerator a character. So you can think of the Legendre symbol as being a character, and in this case, Ramanujan is putting in the Legendre symbol n over 3. So it's 0 if n is a multiple of 3, it's 1 if n is congruent to 1 mod 3, minus 1 if n is congruent to 2 mod 3. If you were to define these coefficients in terms of zeta and L function values. So this is the enigmatic continued fraction, but we've actually replaced q by e to the minus x, and sort of rewritten the continued fraction by multiplying the numerators and denominators and writing this in equivalent form. So the continued fraction doesn't converge at x equals 0. That would be when q is equal to 1. And what Ramanujan does is examine the behavior as x tends to 0 from the right of the continued fraction. So I probably would have put the 3 to the x to the 1/3 on the other side. So then it tells you exactly how this continued fraction is behaving. So it behaves like a constant times 1 over x to the 1/3 as x tends to 0. And Ramanujan figures out what this constant is. But he wants to go further. He writes the remainder, so to speak, as e to subfunction g of x. And then he gets an asymptotic expansion for g of x as x tends to 0. And that's where those coefficients that I defined on the previous screen are given. So here are just a few of them. And then he's still not satisfied. He looks then at what happens to this series. He finds the minimum value of the series as x tends to 0. And he says the minimum value then is asymptotic to this as x tends to 0. So this is a very interesting, very refined examination of this continued fraction as to how it behaves as you approach this divergent point, q equals 1, or if q is e to the minus x as x tends to 0. So the one other reason I mention this is that I've stated a lot of identities in this talk, and Ramanujan is certainly known for his identities, but he also is known for his studying the behavior of how functions behave. So he has lots of results on approximations of asymptotic expansions of continued fractions, series, and integrals of this type. He was very, very good at studying how things behave in mathematics as well as producing identities. So I think with this example, I'll conclude my talk, and thank you very much for coming this morning.
Are there any questions?
Perception of the methodology.
Well, let me say at the outset that he proved things like any other mathematician would. So sometimes, because Ramanujan didn't give us proofs of many of his results, people tend to think he maybe just pulled these out of the air, or they're explained by his goddess Namagiri or something. He might clearly have believed that goddess Namagiri helped him in his work. So I am not discounting something like that. But he proved things like any other mathematician, but in many cases we have no ideas about his proofs. In some topics, we can sort of guess how Ramanujan proceeded. So in particular, in the notebooks, he sort of naturally leads us from one result to another. So you can see, because of this natural flow of results, how Ramanujan might have improved the results. But for other topics, we don't know how Ramanujan proceeded at all. And two of these topics I've mentioned, for the mock theta function identities, although we've now proved them all, none of our proofs, I'm certain, are those found by Ramanujan, because we use ideas that he wouldn't have been familiar with. And then I mentioned these class invariants. Ramanujan computed over 100 of them. And in some of them, for some of them, you can use modular equations to compute them. But for others, they're not computable by modular equations, or if they are, the modular equations were not found or didn't exist in Ramanujan's time. So Ramanujan evidently was able to work in algebraic number fields using maybe some sort of ideas of class field theory, which were later invented. And he had his own way of looking at them, but we just don't know, what that way was. So, those are two of the topics for which we're very much in the dark about how Ramanujan thought.
We've seen, you have plenty of material of, say, Euler or Gauss, for example. Compared to their working to what Ramanujan has done, can we even make any kind of comparison at all on how they have come up with their results or their workings?
Yeah, it's very hard to compare, mathematicians and sort of rate them in terms of, is Gauss better than Ramanujan or Euler? Yeah. In regard to Ramanujan, just because he left so few proofs to us. So if he had published all of his results, like other mathematicians, we would probably have a clearer picture of. But he didn't do that, and actually, I'm glad he didn't, because, well, not only has it given me something to do for 40 years, but also he discovered much more than we would have had. So in other words, if he acted like a European mathematician and wrote down all his proofs rigorously, putting in the epsilons and deltas, etc., it would have taken him a long time to do this, and that wouldn't have been the best use of his time. So he was busy after he found something was true, and he had a sufficient argument for him, to go on to something else. And so I'm glad he did proceed in this way, and we're all the better for it, because we have a lot more results, a lot more beautiful results than we would have had otherwise. So the only thing I will say is that with the finding of the lost notebook and our coming out with putting before the public what Ramanujan did, and with proofs, although they might not be anywhere near what Ramanujan had, in the last 40 years, I think there's been certainly a greater appreciation of Ramanujan, and not only is there a greater appreciation, but his mathematics is, pervading many other areas of mathematics that we have today. So in particular in combinatorics and in physics, many other areas. So it's, when we had celebrated the centenary of Ramanujan's birth in 1987 at the University of Illinois, we had about 30-hour lectures on various topics in modern mathematics and physics that have been highly influenced by Ramanujan's work. So there's just a lot of topics in current mathematics and physics that have been influenced by him. Yes?
Are there results of Ramanujan that are known to be wrong?
So when I worked on his notebooks for a little over 20 years, and I counted them as I sort of went through, and I counted 3,254, but you might count the number 100 or 200 more or less. Of those 3,000 or so results, I found maybe 5 to 10 that were wrong. So I'll tell you about a couple of them. So in Ramanujan's two letters to Hardy, he stated some incorrect formulas in the theory of prime numbers and analytic number theory. And there are various reasons for this. One is that he invented Riemann-Stieltjes integrals by himself, but didn't sort of work with them properly. It was about the same time that they were actually invented, not too many years earlier, by Stieltjes, but he wouldn't have access to that work. And he inverted limiting processes, and without thinking about it, and maybe they weren't always valid. And he also had the beginnings of the circle method in his notebooks, which was developed by Ramanujan and Hardy after he got to England. So because of all these reasons, when he stated error terms for approximations in prime number theory and maybe some similar kinds of problems, his error terms were too optimistic. And so they weren't justified by the mathematics that he did. And so this is where he made some of the errors. I remember one formula where he had a beautiful identity, and it turned out, however, that the regions in the complex plane where the two sides converged did not overlap. And so, therefore, he didn't really have an identity. So there are a couple of results of that type. But for most of us, if we wrote down our findings, we'd have many more than 5 or 10 results, and with a much smaller number.
So the related question is, does this suggest that there is a way of formal reasoning in mathematics which we don't know about? I mean, the question is that.
Yeah. So that's correct. In fact, that was sort of one of the previous questions too. That we just really don't know how Ramanujan thought about many topics. It's for some, we can make pretty good guesses, but for others, we're just totally in the dark. Yeah. Was that your question?
Yeah. So I have one more question. Last one. Does your research suggest that Ramanujan read other literature?
Yeah,
What
that's.
does today do with the sense of,
Yeah, very little literature. So we know some of the books that he studied, before he went to the government college. He probably learned about elliptic functions from some book, which probably was Cayley's book on elliptic functions, although he might have been also familiar with Greenhill's book. Cayley was much more algebraic than Ramanujan. So he might have learned from Cayley what a modular equation was, but Ramanujan's approach would have been much different. Greenhill's book was mostly devoted to applications of elliptic functions. And in his notebooks, Ramanujan does have a few applications of elliptic functions to pendulums, periods of pendulums. And so maybe that's a hint that he did know about Greenhill's book. However, Ramanujan's development of the theory of elliptic functions was much different than anyone else's. So these books didn't really influence him at all. He might have seen them to see that, well, mathematicians are studying these objects. That was enough for him. He would study them in his own way.
Can I ask one more question? The mathematical journals at that time in India, where Ramanujan was posing a lot of problems, also solving problems. What was the level of the mathematics that was prevalent at that time, and how significantly different are the topics that he was actually working on in these notebooks that you have pointed out?
That's a very good question, and I think I can actually answer some of it, or part. So the mathematics that was being done in India at that time was, certainly influenced by mathematics in England. So most, Indian mathematicians were not working as professional mathematicians. If they got a degree in mathematics or a master's degree in mathematics, which was the highest degree offered at that time, they usually got jobs which were better paying jobs than you would get teaching in a college or university. So unfortunately, then the best minds were really using, their abilities in some other area. So I've actually examined the issues of the Journal of the Indian Mathematical Society quite closely in the years that Ramanujan contributed both problems and papers to the journal. Many of in Ramanujan's notebooks, in the early chapters, he was very highly influenced by the mathematics that was being conducted at that time. You will find kinds of topics and formulas which were rather similar to problems and topics that other mathematicians in India were actually doing at that time. And a lot of the problems that were posed, not only by Ramanujan, but by others, not only in the Journal of the Indian Mathematical Society, but the Educational Times, which was published in London, were actually very tough problems. They were not easy problems at all, but they weren't really, you might say, in the forefront of research that was being conducted in the rest of Europe at that time. So, let me just say in conclusion, Ramanujan was influenced in his early work by what was going on at that time. He almost always went much further. In other words, he went much further along the road, got much, much better results than what were done at that time. But the spirit of some of his early mathematics certainly reflected the spirit of mathematics in India in those days.
Are there still any unproven conjectures, Champaigne? Like Fermat's last year kind of conjectures?
Right. Yeah. So, in the notebooks, I think everything has now been proved in the earlier notebooks. And in the lost notebook, there are still a number of results that have not been proved. But so George Andrews and I, over the last several years, are trying to prove everything in the Narosa edition, not only the original lost notebook, but the other fragments that have been found. So I think we're maybe 95% finished, although we haven't written everything up yet. So far we've published 2 books, and we project maybe 5 books altogether to describe the results in the lost notebook. So there are some things that we haven't been able to prove yet. And there are a few things that we just haven't had time to look at yet. Let me just tell you about a pair of results. Yesterday at the Institute of Mathematical Sciences, I lectured on 2 results from Ramanujan's lost notebook. One of which my colleague Alexandra Zaharescu and my former student Sun Kim and I recently proved. The other of which we have not proved yet, but we think we're close to a proof. But we've worked on these for about 6 or 7 years before we actually proved the first one. So that one is one of them that hasn't been proved yet, the second of these 2 formulas. But we think we're now closing in on a proof. And there are a few other results which we haven't had time to look at yet, and there are some results which we can't prove yet. So there's a conjecture in analytic number theory that we're unable to prove. I I've given it to one of my students. Hopefully one of my students will have some insight. There are a couple of formulas which are wrong, but which we feel have correct versions, but we can't find the correct versions. I've sort of been thinking about these formulas for a half a dozen years or so. Certain that there are correct versions that are out there, but I don't know what they are. So we're closing in. We got a few things yet to prove, but most of the things we'll have proofs. But the question really is, how did Ramanujan think of these things? And there we're, very far from what we should be.
So on behalf of the audience here, I'd like to thank Professor Bruce Berndt for his very nice and enlightening lecture on Ramanujan's Lost Notebook. It was very nice. Thank you very much, sir.
Thank you, sir.